So without further ado, it gives me great pleasure to introduce our first speaker, who is Sara Imbriglio from the Department of Mining and Materials Engineering. And Sara's working with Professor Richard Chromik and Professor Raynald Gauvin on her PhD research. And Sara's going to talk to us tonight about how we can reduce the energy and reduce the waste during the manufacturing of advanced materials through the cold spray process. Sara.
Industrial development has allowed us to significantly improve our quality of life. And that's ultimately because the products output from these industries are what allow us to have the things we have and do the things we do. But if we are to keep moving forward in a sustainable way, we need to make sure that we answer one key question. And that question is, how do we achieve harmony between the industry and the environment? And to do this, we need to consider every step of the life cycle of a product we're designing. And that's from where are we getting the materials, to how are we making it, how are we producing it, and then eventually how will we dispose of it. And in every single one of these steps, you need to think, how am I affecting the environment, and how can I ultimately reduce that environmental impact? But I want to focus here today on one example that pertains mainly to manufacturing and the products that we're making. And you'll notice here that the two examples I've used to represent the product come from the transportation industry. And that's because the transportation industry and the manufacturing industry have one key thing in common. They're wasting 20% of the world's energy. Can you guess how? To overcoming friction. That's right. We are losing 20% of the world's energy to friction. This has huge environmental and economic consequences. Think about the cost of the energy. Think about the energy we're producing is coming mainly from fossil fuels, and therefore how much toxic gases we're emitting without even using that energy properly. And finally, with more friction typically comes more wear, and more wear means more waste. So how do we overcome these issues? Well, it turns out there's an entire field of study focused on some issues that revolve around friction and other type of issues similar to this. And those are, and this field of study is surface engineering. And surface engineering focuses mainly on the development of high-performance surfaces. And this can be to overcome any type of environment. But the type of things that we tend to look at are how to increase wear resistance, increase corrosion resistance, and also reduce friction. But to do this, we need to look at both what materials we'll be using and what processes will we make these new coatings with. So when we choose the materials, the first thing we need to think is, what materials do I have available to me? And the three major classes that tend to come up are metals, ceramics, and polymers. Now, these materials, unfortunately, on their own, don't necessarily offer the type of properties that we need. And that's because, for example, each of them have their own advantages and disadvantages. For example, a metal might be very ductile, but in consequence is not very hard. Or a ceramic is very hard, but then is not very ductile, and that's why it results in fracture typically. So it turns out that if you combine these materials in order to form a composite, you can actually take advantages of each of the material and tailor a new material that will give you the properties you need. In my work, I focus on metal-ceramic composites. And we often refer to these as metal matrix composites. And these do offer us increased hardness, increased wear resistance, increased corrosion resistance, and even self-lubricating properties. And that goes back to that friction issue. If we could make self-lubricating properties, we can reduce friction and even try and reduce the need for toxic lubricants in various industries. So how do we make these metal matrix composites? The technique I'm proposing here today is the cold spray process. The cold spray process is actually quite a simple technique and has only 3 major components. The first one is the high-pressure gas. The second, the powder feeder. And the third is the cold spray gun, or we also refer to this as the cold spray nozzle. The gas coming from the high-pressure tank will travel both towards the gun and towards the powder feeder. And the portion going towards the gun directly will be heated. And you'll see in this short video how all of these components work together to ultimately deposit a coating. The gas that's going directly to the powder feeder will allow the powder to be injected into that gas stream. Once it reaches the nozzle, it recombines with the heated gas and can then go through the nozzle and achieve supersonic velocities. The particles coming out of this nozzle then impact the part and can create a coating. But why cold spray? Why not any other technique? Well, it turns out the cold spray process is quite environmentally friendly. The gas we're using is nitrogen. Nitrogen is found in the air that surrounds us and is therefore non-toxic to us. The powder that we're using is not melted. These are deposited in their solid state. And by not melting these metals, we are not getting any byproducts. But another interesting thing is that the heat input that we're putting in, so the energy that we're putting into the process, is actually not significant since we're not melting that powder. And also, there's various research being done to optimize the nozzles to try and increase velocity simply through the nozzle characteristics, rather than increasing velocity through an increase in temperature. So if we do this, we might eventually even remove the need for that heat input. And another thing is that this is an additive process. So we are getting nearly 100% of the powder we're trying to deposit it in the coating. But in order to do that, you need to understand how these coatings are being formed. And you need to understand the deposition mechanism, how they're bonding, and all kinds of characteristics like this. And that's where work like mine comes in. But just a little side note, this coating technology is not limited to thin coatings. We can actually grow features onto a part because we can make thick coatings. And we can use this even for repairs. But how do these particles get deposited? I mentioned, in order to get that 100% deposition, you need to understand the bonding mechanism. In metal-metal interfaces, the bonding mechanism is mainly through what we call plastic deformation. This plastic deformation is basically a term that we refer to as a permanent deformation of a material. And it's really that impact that induces the plastic deformation and results in bonding. And in metals, plasticity is really well understood. Take, for example, a fork. If you try and bend the fork, it'll maintain its shape. And it's the fact that it maintains that shape that is called plastic deformation. But if you think of a cup, can you do that? Especially in an impact scenario, what you would mainly expect to happen is this. But luckily, we can create metal matrix composites by cold spray. So let's see what's happening there. When we spray these coatings, we have both metal and ceramic powder being sprayed simultaneously. And when we spray these, we have 4 different types of interfaces. A metal impacting a metal, which bonds, as we explained, through that plastic deformation. A ceramic impacting a ceramic, which unfortunately does lead to fracture. And finally, we have the metal-ceramic interfaces. And these metal-ceramic interfaces are unfortunately not well understood. And that's what my research focuses on. When I'm trying to look at these metal-ceramic interfaces, there are 2 things that I'm focusing on at the moment. The first one being is, what velocity do I need in order to achieve deposition? Just to give you an analogy here, these particles technically need to bond through plastic deformation. And as I mentioned, the ceramic won't plastically deform. So in that metal-ceramic interface, what do I need to get a bond, and why is it bonding? You could think back to when you were a kid playing with Play-Doh, and you threw it at a wall. In some cases, it bounced back at you. But if you threw it hard enough, it could actually stick there. Well, that's exactly what we're trying to see here. What is hard enough to get bonding? And we study this by changing the ceramic and seeing how the type of ceramic that we're using will influence the critical velocity for deposition. But once these particles have been deposited, we need to know how well are they bonding? How good is that adhesion strength? And once again, we study this by looking at how the type of ceramic will affect it, and also how surface roughness could affect it. So let's start with the deposition velocity and looking at how the deposition velocity is affected by the type of ceramics. To do this, I did experiments at MIT. These experiments were basically to spray those particles towards the two ceramics and capture the impact with a high-speed camera. The ceramics that we used for this were aluminum oxide and silicon carbide. And once this metallic particle passed in front of the high-speed camera, you could see when it will bond and when it won't. So in a case that it didn't bond, this is what the images would look like. Effectively, you can see that the particle is impacting at a relatively high velocity and then rebounds. And the rebound velocity is actually lower than the impact velocity. And in fact, if you take a ratio between the rebound velocity and the impact velocity, you get what we call a coefficient of restitution. And this is basically a measure of how much energy is lost during that impact. So it's a quantification of the amount of energy you're losing due to plastic deformation. And if you were to take this particular experiment and plot it on a graph with respect to the impact velocity, you would get this. And if you repeat this multiple times, you would get a series of points that show you how that coefficient of restitution varies with impact velocity. And eventually, you'll get adhesion. And this is an image that we observe when the particle does not rebound. And what you'll see is that on this coefficient of restitution graph, these will appear as points on the x-axis. And you could see that at around 600 meters per second, you'll get adhesion. But these are the results for titanium deposited on aluminum oxide. What happens when we deposit on silicon carbide? In fact, what we observed was that the critical velocity is closer to 800 meters per second. So changing the ceramic has a significant influence on the velocity you need to be spraying these at. So now let's look closer at the particles that bonded and how strong is the adhesion strength and how the type of ceramic will influence it and how surface roughness will influence it. To do this, we sprayed the single particles towards aluminum oxide with different surface roughnesses and then repeated the experiment with titanium deposited on silicon carbide. And at this point, you might be asking yourself, well, if you're depositing these single particles, how can you test their adhesion strength? We have a specialized equipment to do this. And this equipment effectively comes and removes the splat, or the splat is what we refer to as the particle bonded to that part. It comes and removes it and can measure that adhesion strength. And the results we've seen were actually quite interesting. The adhesion was higher to the low surface roughness aluminum oxide than to the high surface roughness aluminum oxide. And this is kind of counterintuitive, because if the bond was only mechanical, you would expect that with more surface roughness, it would kind of be clamped in there. But that's not what we're seeing. It's not giving a higher bond strength. Another analogy would be if you're trying to remove gum off a glass or off of a carpet, usually the higher surface roughness gives the higher bond strength. We're not seeing that. Also, changing the substrate to silicon carbide allowed us to compare how aluminum oxide behaves and how silicon carbide behaves. And what we saw was that the silicon carbide bonds with a much lower bond strength than the aluminum oxide in any of its surface roughnesses. And why do we get this low bond strength? To understand this, we need to go to the scanning electron microscope and analyze the cross sections of these interfaces. And what we can see is the morphology at the interface, and we can understand if there's any chemical changes or if the composition changes at that interface. But we're actually going to need to go even further than that and see at the atomic scale if there's any chemical interaction to explain why surface roughness has a counterintuitive effect and how the different ceramics play a role in here. We saw that changing the ceramic had an effect on both adhesion strength and on the velocity you need to deposit these. But once we've completed all of this work, we're going to need to think back and see how these single particles reflect in a full metal matrix composite coating. But this work will help us improve those metal matrix composites. And by improving these metal matrix composites, we can go back to that manufacturing and transportation industry and see advantages in reducing friction. We're going to reduce our energy consumption, reduce the amounts of toxic emissions, and also reduce waste. But just before ending, I'd like to say one more note about the manufacturing industry. Today I presented a technique that is not only created for these metal matrix composites. It's actually an environmentally friendly technique with other applications. And the study of these metal ceramic interfaces can allow us to use this environmentally friendly technology to even potentially deposit metal coatings on ceramics. And this could have huge implications in biomedical industries because, for instance, titanium and aluminum oxide, which are showing the higher bond strengths, are both biocompatible materials. This can help us in improving artificial joints. We can even think of electronics industry. We can generate customizable circuitry or metal ceramic seals. And I'm sure there's millions of other applications I haven't even thought of. And it is the development of these environmentally friendly manufacturing techniques, thinking about the materials we're trying to produce with them, that are bringing us one step closer to achieving harmony between the environment and industry.
Thank you very much, Sarah. So we have time now for one or two questions. Do we have a microphone? Yeah, perfect. Any questions? At the back here?
Which one of the two ceramics has a higher porosity?
They're actually quite comparable. I've cross-sectioned them, and they're sintered ceramics, so we're not seeing a significant amount of porosity in there. One thing that we did see, though, was that when we impact the silicon carbide, the interface tends to show more porosity, and that's probably because there's fracture occurring. So I don't think it's related to porosity necessarily, but I do think that the mechanical properties of the ceramic itself has more of an impact.
Any other questions?
Yes.
Jim?
Can you comment about the production of the powder, the same salts?
So the powder that we the powder that we're using was plasma atomized, which is actually a Montreal invented technology. But I don't know exactly what you would like to.
Well, in terms of the larger impact, so if you look at the full life cycle of the process, you describe it very well, the
Yeah.
savings of the process itself. But I don't think you commented about the production of the powders.
I haven't considered it, to be completely honest, but I do think that the technology is advancing significantly, especially with advances in additive manufacturing. So the powder we are using is the same powder you would use in additive manufacturing. So I do think that maybe at this point in time, we are not at a very environmentally friendly level at the production of powder, but we will eventually get there.
Maybe more to come on that later. So with that, I'd like to thank Sara again.
Thank you.